Welcome back, ladies and gentlemen. Today we're going to talk about parent functions. Actually, more specifically, we're going to talk about how to transform a parent function. So before this video, I'm assuming that you already have a pretty good grasp of what each parent function looks like. And there's another 16-minute video, or actually a 26-minute video on my website for the first 16 minutes of said video on my YouTube channel. Goes over what each parent function is and what it looks like and how it behaves. So if you don't yet or aren't yet familiar with all of these equations and what they look like when they are graphed, such as over here, please go ahead and get that information in your head solid first, because now what we're going to do is we're going to take all these shapes that exist over here and we're going to move and stretch them according to some sort of transformation. And that's what a transformation is. It's a general term for doing anything to a parent function that changes either its shape or its location. And if you take a generic function in function notation, like the f of x notation, and you add or you insert numbers in specific places with specific operations, they will have consistent outcomes in how you do it. So right here is the general form of all the things that you could possibly do to a function. There's an a, b, a c, and a d. And depending on where you put the number and how you attach it to the function, it will dramatically affect how the function moves or is stretched. Now, there's a distinct inside of a function and outside of the function. I want you to pay attention to those two, because stuff inside the function does the opposite of what you would think it would do, whereas the stuff on the outside of the function does exactly what you would think it would do. It's very logical. Now, this particular general form right here with all four items in it, it's actually a little more complicated than we usually have to deal with. Now, so we're going to eliminate this b right here. We're just going to ignore it. Some functions will have a coefficient sitting right here in front of the x term inside the function, and if that's the case, that's where that came from. It is a b value, but the b value gets distributed onto both the variable and the c term. So if you have a coefficient inside of a function, know that there's a little bit of extra work there. For our purposes, though, we're going to move to a function that is much more simple. Okay, so with the b term in there, let's look at this one because it has everything in there. But the a term out front will make it stretch vertically. So it'll make it steeper or less steep, or basically stretch or compress it in the vertical direction. The b term does the same thing but in the horizontal direction, and it does the opposite of what you would think it would do. If you throw a negative either on the outside of the function or the inside of the function, on the outside of the function it's going to flip it vertically. On the inside of the function it's going to flip it horizontally. So inside the function it would flip it across the y-axis. Outside the function it would flip it over the x-axis. Okay. The c and d values are actually pretty easy to figure out. The c value shifts it left and right, and it's inside the function, and it does the opposite of what you would think it would do. So if it's a positive 4 in there, it actually moves it to the left 4, and so on. And the d value is often easy to identify as well, because it's just plus or minus tagged on at the very end of the function. Sometimes they put that number first, so it's a little confusing, but other than that, it's not too bad. We're going to focus on this form, so we're just going to eliminate the b. We're not going to deal with anything else. So we're just going to deal with the a, the stretch or the flip vertically, the c value on the inside, which will shift something left or right, but it'll do the opposite direction depending on its sign, and the d value will shift something up and down. Okay. Here's a couple examples. These right here are all examples of putting the number inside. So all those fours are a c value, and everything out here you can see that the 4 is tacked on at the end, so that would be a d value. So here's a few of the parent functions over on the left hand side, and you can see how each has been modified to move it in either left 4, right 4, up 4, or down 4. So you can see the difference between putting a number inside the function versus outside the function, and what effect changing the sign on the inside versus the outside has on the function. So right here, for instance, we have a positive 4, but it's moving left 4. Here we have a negative 4 on the inside, and it's going to the right 4. But if we put the 4 on the outside of the function rather than the inside of the function, which, well, maybe the linear function is a bad example. Let's look at the x squared function. There you can clearly see, right here you can clearly see the positive 4 is on the inside. Here the negative 4 is on the outside. Sorry, the negative 4 is on the inside still, but over here, say, the negative 4 is clearly on the outside of that squared piece, okay? So when it's clearly on the outside, it's going to move it up and down. When it's clearly on the inside, it's going to move it left or right. The next thing I want to take a look at is if you put a number out in front. So this would be playing around with the a value, okay? So all these are a value changes. If you throw a negative out front, what it's going to do is it's going to flip it upside down. So if you had a parabola facing smiley face style, facing upwards, it's going to flip it over to a concave down situation or a frowny face situation. And it goes all the way through the whole gamut of what your parent functions might be. If you put a number like 4, if you put a number like 4 in front of the term, what that's going to make it do is it be 4 times as steep or 4 times as tall as it normally would be. If you compress it by putting a number smaller than 1 in front, that's just going to make everything 1/4 as steep. Basically, it's like taking your final y value and just saying, oh, we're going to knock that in 1/4 or times 4, depending on the situation here. Okay, I would like you to go to our website, and on our website there's a link to the Desmos graph that I'm pulling up right here. And there's a bit of background work being done here. I have a function being defined, f being x squared, and then I have g of x being defined with all the little slider values that I can use to change the shape or location of that function. The benefit to it doing this way is I can go back and I can change what f is, and I can actually transform any of the parent functions that I want. But let's just play around with a parabola for now. If I grab this slider for the a value and I increase it, so a value is now 5.5, 5.6, there we go, and up and up and up it goes. You notice that it gets a lot steeper. If I bring it back down, you'll notice that it starts getting wider, and if I drop below 1, it gets much, much wider. As soon as I go negative, the parabola is facing downwards, and if I go really negative, it's going to go steeply downwards in both ways. Okay, the standard number for that, it would be a 1.0. I'm not going to mess around with the sliders because it's just too difficult. If we move on to the c value is on the inside of the function, so this should move the function left or right, and right now c is 0. If I crank that up to say a 2 or a 2.6 in this case, you'll notice that I am subtracting, according to our formula, I'm subtracting 2.7, but you can see, and if you trace the vertex, you can see that that got moved over to the right, however much my c value is. If I move it left, okay, so now we're subtracting a negative, so really it would appear in a formula as x plus 6 on the inside, or plus 3 on the inside, but I've moved to the left. So hopefully that's not too confusing. And then the d value, of course, moves up and down. Now, I've produced this Desmos graph for you so that you can copy it and you can play around with it. So, for instance, we don't have to keep that in x squared. We can do something a little bit more interesting, maybe like an absolute value, which you can type, clearly not the way I type it in. Here we go. Absolute value of x, and you can, Desmos knows ABS, parentheses, and now you can see we're basically doing the same thing, but we're doing it with an absolute value. So if I change the a value here, the absolute value function is getting steep, and it'll flip, and it'll stretch downwards as well. So we can play around with all these values again in the same way. This is left and right still, it's just that I'm using an absolute value, and this is an up and down movement, it's just that it's an absolute value instead of a parabola anymore. One of the main features is that you can, or one of the main telltales of what sort of function is just the shape of it, but what happened to it, try to trace a point, if you can, that you know where it used to be. Like right now, it's very easy to see there's a vertex at like 1.2 and 2.5. If you can track a point like that, you'll have a lot more success in trying to figure out what has been done to the function to change it. Okay, I'm going to move on. Go back to Notability here. And we should be able to look at these functions and we should be able to tell what has been done to it and what it generally looks like. So when you look at an expression like this, you should see this indicator right there. That is a cube function. So there should be, in your head, you should say, oh, this is going to be a cubic function. You know what the cubic function looks like because you know your parent functions. It looks like that, except better. And then... And then what has been done to this function? Well, we've got a -1 here, so that means it's gone to the right 1. We've got a +10 here, so that's up 10. And we've got a 2 out front, so that means it's twice as steep or as tall. However you want to phrase that is just fine. If we move on to the next one, maybe change colors for this one, why not? We'll go... Our indicator here, the unique identifier to what function family it is, we've got a cube root now. So now we basically take that cubic function and we turn it on its side, and we've got something that looks like that. Except this function, now we have a plus 5 on the inside, so that's left 5. We've got a minus 7 on the outside, so that's down 7. And we have a negative 1/3, so that means it's got a vertical flip. So that means that this function has been flipped vertically over the x-axis, or it's going to go downhill as we travel to the right, and it's 1/3 as tall. So it's got a compression on. This is an absolute value. I think we did one of those. I think we're good on that. But basically, you should be able to look at an equation and identify what has been done to it. And ultimately, we need to be able to graph these things. So on our next sheet of notes right here, I have provided notes on the website, so if you want a space to graph and all that, it is there for you. So right here, I identify, hey, it's a cubic. So I'm going to just switch colors here. I identify it's a cubic, and I've got a minus 4 on the inside, so I'm not even going to do this table. I don't like tables. So I've got a minus 4 there, so I'm going to go right 4, and I've also got a d value of 2, so this is up 2. But other than that, it's basically a cubic function. So our parent function for a cubic function, it goes through 0, 0, 1, 1, and 2, 8. Those are some good points to know for the cubic function. Almost all graphs go through the origin, and either 1, 1 or -1, negative, somewhere in that box, one direction or the other. And then I'll also mark this other point over here at -2. So this is the parent function right here. I'll try to do my best job drawing through. Oh, that was bad. Okay. That was so bad, I'm going to redo it. All right, so if we try that again, I'm going to put in my landmark points again. This is just the parent function I'm talking about here. And I can draw that in, and I know that that is where my cubic function normally lives, okay? But we know that we have to go to the right 4 and up 2. So all these points that I have here, I'm going to go to the right 4 and up 2. So that's going to be my new origin right there. And then I go basically use the same shape because there's no stretch on. So I would normally go over 1, up 1, and down 1, back 1, and then over 2, up 8. So I'm going to go all the way up to 10 now. And for this point that I would normally go back 1, down 1, I'm going to go back 2 and down 8. That'll land at -6 right there. And that's where my new cubic function lands, right there. And again, I will get better at drawing those as I get practice. But we're going to move on from that. All right, let's do one more, and then we'll be done. So let's look at this absolute value function. This time I have an a value in there. So you can see that we've got this -4 out front, so I have a vertical flip. Everything's going to be 4 times as steep. 4 times as steep. So it basically means that instead of the absolute value function, so basically our normal parent function would be right through the origin, right here, and then out the other side. But if we perform that transformation, we also have to go, let's see, we also have to go left 1 and up 5. So I'm going to mark that new origin. So I'm always going to do my translation first. Left 1, up 5, right there. And then I know that I have to go down instead of up because I have that vertical flip on. And then I also have to go 4 times as steep. So normally I'd go over 1, up 1. So I'm going to go over 1, down 4. So I'm going to land right there at 0, 1. And the same thing over on the other side. I'm going to mirror that over. So there's my first 3 points, and I can go down 4, over 1 more time on each side to get my next points. And now I can draw a straight line through the points. Line it up through these. Here we go. And there is my transformed absolute value function. Now the idea here is that you should be able to do this with any of the parent functions no matter what shape there are. So it's good to know what shape they are and where the parent functions are located. Pay attention to their behavior around the origin so you can move where that origin is and then work the scalar vertical change from there. So go find your new origin and then move according to that new scalar out front if there is one. With that, I'm going to close this video and I'll see you in class.